Okay, go ahead, Jacob.
Good morning, everyone. Thank you for joining today. Today, we'll be presenting our project focus on concentrating solar power, or CSP. Our goal is to walk through the design and performance analysis of our CSP thermal power plant. We'll explain why CSP is promising technology with a large-scale renewable generation and how we tailored our design for maximum efficiency. Concentrating solar power technology captures solar thermal energy using mirrors and lenses and converts it into electricity. Unlike photovoltaic systems, CSP can store energy for use after sunset, making it highly dispatchable. And this project will analyze the key components, including parabolic troughs, heliostatic fields, and thermal energy storage systems. The importance of CSP lies in its potential for enhancing grid reliability, increases renewable energy adaptation, adoption. Our main objective was to design the system that optimizes performance while being economically and environmentally feasible. So our criteria for site selection, um, we selected Southern Nevada as our site because it offers some of the highest direct normal irradiation levels in North America, between 7.5 and 8 kilowatt hours per square meter per day. The region experiences constant sunlight and has vast areas of flat land, publicly managed land available for renewable energy projects. The proximity to existing grid infrastructure significantly reduces the additional cost of construction. Nevada state policies also strongly support renewable energy development, aiming for 15% renewable energy by 2030. All these factors make Southern Nevada an ideal location for CSP development. Our plant design is centered around the use of parabolic trout collectors, which focus sunlight onto a receiver tube filled with heat transfer fluid. This thermal energy is stored in molten salt tanks, allowing the plant to produce electricity even when the sun isn't shining. The system operates on the Rankine cycle, where the heated fluid drives the turbine connected to a generator. Compared to photovoltaic systems, CSP plants offer dispatchable power, higher operating temperatures, and better thermal efficiency. These features enhance the grid stability and reduces reliance on battery storage. So here are some of the numbers behind our design. Um, our collector field area is around 200,000 square meters, which is a scale figured based on successful existing plants like Nevada Solar One. The plant operates in an optimal efficiency at 75% and a thermal to electric conversion efficiency at 35%. Given Southern Nevada's high DNI, we calculated an annual out input at 2,850 kilowatt hours per square meter. The plant's rated capacity is 50 megawatts, allowing it to contribute to substantial renewable energy to the grid. These values strike a balance between scalability and cost efficiency and performance. Using our parameters, the plant will collect around 570 million kilowatt hours of solar energy annually. After accounting for optical losses, about 427 million kilowatt hours are converted into thermal energy. Converting that thermal energy into electricity results in about 150 million kilowatt hours per year of electric output. This translates to an average output between 17.1 megawatts, resulting in capacity factor of 34%. While not 100% is still strong numbers for renewable technologies, and this demonstrates good year-round reliability. Although CSP, so this is some of our economic feasibility analysis. Although CSP requires significant upfront investment due to collector fields, storage systems, and supporting infrastructure, it benefits from extremely low fuel costs. Sunlight is free. Maintenance costs are moderate, involving cleaning mirrors and maintaining the turbine system. Access to public land through federal leases in Nevada significantly lowers land acquisition expenses. Over time, long-term savings outweigh the initial cost because CFP plants can reliably operate for 25 to 30 years with minimal fuel costs. Additionally, policy incentives and technology improvements are continuously driving down the cost per kilowatt hour. CFP plants have major environmental benefits, especially when compared to fossil fuel generation. They produce no carbon emission during operation, consume much less water when dry cooling and or hybrid cooling methods are used, which is crucial in desert regions like Nevada. However, large land footprint over 200 square kilometers in our case could potentially distribute disrupt local desert ecosystems. Our site selection process emphasize avoiding sensitive habitats and use public land already designated for energy products. This way, we can minimize ecological impacts while still delivering renewable energy. Building strong community support is crucial for the success of renewable energy projects like CSP. Early engagement with local communities help ensure the project aligns with their values and their expectations. Through public land permitting processes, agencies like the Bureau of Land Management require public input, stakeholder consultations. By involving communities early, we can address concerns, build trust, and ensure more equitable and acceptable project outcome. And this also strengthens overall public support and a broader renewable energy incentives. In conclusion, CSP offers reliable, large-scale solutions for clean energy generation, particularly in regions with high solar potential like Southern Nevada. Our analysis shows that with proper site selection, efficient design, and community engagement, CFP can deliver significant environment and economical benefits. Future research should focus on improving thermal storage material, exploring higher efficiency working fluids, and integrating CSP with smart grid technology. With stronger public support and continued technology innovation, CSP may play a major role in global shift towards sustainable energy. Thank you.
All right. Thank you, Jacob. Any questions for Jacob? So I have questions about, did you mention about dollar or, financial analysis at all?
I did not, but
Okay. So who are your members?
um
Who are your group members?
sorry, I have their names written down. I'm sorry. You can go ahead.
Nick's member, Colin, and
Yeah. Howie.
Howie.
Also a member.
Okay, so 3. Is that 3? 3 people?
Yep.
Yes, 3 interns.
Okay, very good. Yeah. So you finish your report and could you submit your presentation as well?
Yeah.
So that I can post it. What about the report?
Yeah, the report is done. I'll go ahead and submit that.
Okay. Very good.
Is there a place to upload the? Oh yeah, never mind.
No.
Yeah, I've already submitted the presentation.
Okay, very good. Yeah, it's the same spot, just submit the same folders.
Yeah.
So anyway, if there's no questions, the second one, Jack, you ready?
Yeah, I'm ready. Let me get it set up.
Okay.
Sorry, I accidentally got out of it.
Okay, it's okay. You need to share your screen.
Yeah, I just requested. It says sharing is not turned on. I think because I ended up leaving and getting back, I don't have the co-host anymore.
Oh, I see. Okay, let me see. Let me see. Ah, yeah.
Okay, let's see. All right, can you see the screen now?
Yeah.
All right, I guess I'll get started now. All right, good morning, everybody. My name is Jack Condra. I'm doing my project. Well, I guess my undergraduate students are Mason Barnes, Parker Barabum, and Preston Malone. And our project is a cost-benefit analysis of a fixed axis versus a single axis tracking PV system on use for the rooftop of a commercial warehouse in Auburn, Alabama. So a little bit about photovoltaic power. There's these panels, they're composed of hundreds of little cells that produce electric current through light shining on the junction of two different substances. By putting a large number of them together, solar energy can be converted to renewable energy. They can provide a system like a house with a localized energy source, or for a more large project like a PV plant, it will provide that plant with the ability to send energy to the grid. Yeah, and just be another source on the grid. So I mentioned fixed axis and single axis tracking designs. So fixed axis, or as you could kind of guess, they are set to a specific tilt angle, while single axis trackers, they rotate along an axis, either east-west or north-south. And some of the pros of a fixed axis PV system would be a lower cost, a higher durability, and lower maintenance. A lot of this has to come to the fact that it doesn't have as many moving parts that a single axis tracker has. While a single axis tracker has a higher energy yield, better performance and efficiency, that's due to it being able to track the sun and kind of better align itself to be as optimal as possible for all hours of the day. Although they have a higher performance, they have a higher upfront cost as well, due to all those extra components needed for that tracking system. At the bottom there, you can kind of see the way it rotates in the pictures. All right, so I mentioned I would do this for the rooftop of a commercial warehouse. The thought behind that would be it would provide that warehouse with an extra source of income, allow it to be a little bit more self-efficient as well. And for the example site that I was using, it is a Walmart Supercenter down on South College. I feel like most of us have been there before. And that's like the picture of it right there. I chose Walmart because their designs are typically pretty standard across the country, although they might be a little bit bigger in some shops and a little bit smaller in other ones. They have a pretty uniform nature to them, and if it works well for one Walmart, that could be carried over for other stores across the country. One of the benefits of being on the roof is there's minimal shading, since it's up in the sky, like 30 feet higher than it normally would be. There's no trees that really shine on it, and it's flat, so it's an optimal space to put those mounting systems for the modules. So I used Helioscope for most of my designing for this project. It is a software used by commercial PV plant designers. So they use it for designing a PV plant in a field, or even for more commercial options, for actually more residential options for houses. And for my design, I used the Trina Solar TSM PD14 320 panel modules, as well as the Sunny Tripower 24,000 TL US inverters. And I picked those because they're pretty standard in the industry. They had a reasonable price and they're reliable. So I felt like it fit for this project. And Helioscope, it helped me with the way I arranged the modules on top of the building, understanding the different spacing and how to make sure it has as little losses as possible. So this picture here shows the shading analysis calculations. So all of it's green, which means that there's no shading. It's highly efficient. If it was like all the panels are really, really tight together and there's a ton more, then it would be all like red. It'd show that it's not efficient at most times in the day. I created two designs. I created one for fixed axis and one for single axis. It was a little tricky getting the single axis to work due to there being a feature, but I didn't have access to it as having a student version of the application. And I tried to get access, but they wouldn't give it to me. They wanted me to pony up the money. But I found a way to work through it by finding what the ground coverage ratio would be for a single axis system and letting that kind of be the basis for shifting that fixed axis design to be a little bit bigger and then incorporating extra costs and more of the financial analysis that's further on. And all the weather and solar conditions were from a station 2 kilometers away, so pretty close. And I tried to make sure the loss was less than 4% on both designs. This is kind of what it looks like for the mathematical modeling. So once you create that project, that design, it calculates the nameplate value, the performance ratio, a lot of this information where you can know the performance of the system. And this is kind of what it looks like, some of the different little tables it gives you. So there's system metrics, and it shows the nameplate value, performance ratio, and to the right, there is the irradiance and energy as well. So this here kind of summarizes all the information for both of the systems. So although the single axis system has a higher performance ratio and a little bit higher specific yield there, due to the fact that the single axis tracking systems require a little bit more space, there's less modules, which affected the annual production and the total amount of energy produced and power produced. So last step was the economic feasibility analysis. So I did one of these for the fixed and the single axis systems. And I was able to calculate the initial cost of the project, payback period, the return on investment, and the internal rate of return. So some of those numbers are the initial cost was 2.6 million, payback period 7.3, and the return on investment was 228%, and the IRR was 13%. For the single axis, this one was a little bit trickier due to me not being able to add the single axis tracking. I approximate the additional cost for adding tracking per panel for single axis versus the fixed axis cost was between $80 and $120. So I estimated it to be about $80 and added that on to the total cost of that system. So the total net cost, factoring that in, as well as subtracting the incentives, was 1.87 million. Payback period was a little bit longer than the fixed axis at 8.1, and the rate of the return of interest was 195, which was less as well. And so comparing these two projects, there's some factors that I was considering. So some of the really big important ones include annual production, efficiency, return on investment, system cost, space utilization, and maintenance. Now we'll see where these kind of line up for each of the systems. So annual production, that was the first one. It went towards fixed axis. It was able to produce more power. So that one's kind of a no-brainer. Efficiency, those single axis systems were more efficient if you looked at that performance ratio in that slide a couple ago. Return on investment, this one was kind of surprising to me, but the fixed axis system had a higher return on investment. That was probably just due to the sheer, just a lot more modules that design had versus the single axis. It kind of overrun the efficiency in the single axis one. System cost, the single axis one was cheaper to build, so it has that benefit there. Space utilization, we were able to fit a lot more panels that produce more power on the fixed axis design than the single axis. Maintenance, this one was pretty interesting to me because although single axis designs, the tracking systems cost more in the long run than fixed axis systems, I considered the fact that there were almost double the amount of modules for the fixed axis system and how that would play into that. And after doing some calculations, I realized that if the single axis maintenance costs are more than 1.6 times the fixed axis costs, then the fixed axis design was cheaper in the long run. So after looking at that and the fact that the typical range for single axis over fixed axis was 1.6 to 2, there's a high likelihood that that value was higher than 1.6. So the fixed axis would be also cheaper in maintenance as well, even though there's more panels. So what is the verdict after looking at all these different bubbles? The fixed axis design is better. Though if money is really a factor, that initial cost, if that's a huge deterrent, then the single axis design would be better. But the return on investment and the amount of production makes the fixed axis design better if that wasn't the first consideration. So now that I talked about that, here are a couple more slides about the environmental impact and the regulatory impact. So some things to consider for the environmental impact of our design. We have to follow all the federal, state, and local guidelines in order to make sure it keeps the environment safe. So Auburn, the only ones that really affect it are about stormwater management as well as mitigating runoff impacts. So how rain hitting the PV plants, if that would affect the rain going to the groundwater and it being kind of a little bit polluted, we want to minimize that. So that is just something to consider, something that all PV plants have to consider as well. Some other things are construction environmental impact. And one way to make sure that that is as sustainable as possible is to minimize the travel of different components being sent in from other countries or from the other side of the country, and making sure they're sourced locally, which minimizes the carbon emissions of all those transportation systems. And then panel disposal, that's a big factor to consider, and that must follow all federal and state guidelines for proper disposal or recycling. On the regulatory side of things, locally, Auburn has a couple different laws that affect it. So there's a solar photovoltaic guidelines that we need to follow. And that's just mainly letting them know where the plant's going to be, how large it's going to be, and just kind of keep it on their radar. That would be important. So if a storm came through and it knocked out the distribution lines and then they didn't consider where these PV plants are, it might accidentally send in voltage back on that line when they thought there wasn't any production, and it could affect like harming a lineman. And it's just kind of good in general for them to understand where all these plants are and how it would affect the grid. Also got to consider there's a height limit of the system due to being a height limit in the city of Auburn. That's not really an issue here. The state, there is an Alabama Residential and Energy Code, which is a very broad range of guidelines that need to be followed. And then nationally, PV plants must fit wind resistance guidelines, especially since it's on a roof. The roof structure must be able to hold the dead weight of those panels. And it must follow the standards for mounting systems, for photovoltaic systems. And then there's also, in very, very general, International Building Code, National Electrical Code, and International Fire Code that need to be followed. So that's kind of the gist of the entire project. Any questions? Thank you.
Thank you, Jack. Any questions for Jack? Yeah, I wonder if you probably should consider sending to the local Walmart and also to the headquarter Walmart, your report, your presentations. Who knows, something might come up, something good might come up,
Mhm.
So, perhaps you and your group can send it out. by email or whatnot. Okay.
Mhm. Yep.
All right. Sounds good. So the next presenter will be Sriya. So let me see if Sriya got the. Okay, you got a co-host, so you should be able to share.
Share the screen. Yeah, am I audible?
Yeah.
Yeah. Yeah. So,
So put
yeah,
it on the.
yeah.
Yeah. Okay.
So today our project is on operation of islanded microgrids using marine hydrokinetic technologies. So before I start with the definition of an islanded microgrid, I would like to share some light on what is a microgrid. So a microgrid is an independent system that is capable of operating independently or in conjunction with the main grid. So microgrid usually has support from the main grid. Today we focus on just the islanded microgrids. That is, it is a self-contained energy system, operates without a main grid, and it uses local power sources known as the distributed energy resources and internally, and these are ideal for remote areas. So key DERs for an islanded microgrid would be a solar panel, a biogas generator, geothermal energy or marine hydrokinetic energy waves, or even a storage system such as a battery energy storage system. Again, the need of islanded microgrids is to access remote areas such as a local hospital or a military base. It is very much resilient and it can help you during a grid failure. Has sustainability, enables clean energy adoption through solar, biogas, and geothermal and hydrokinetic resources, and is efficient, has uses smart controls, optimization, and and is very innovative, a real world testbed for new energy technologies and storage systems. Now, this is an ideal picture of an islanded microgrid. Here we see a small community. It is surrounded by water. So we have hydro as DERs for renewable resources. As DERs, we have hydrokinetic. We have a wind source over here. We have solar panels as well. And as a traditional, for a non-renewable resource, we have a traditional diesel generator. These help you during any fluctuation of any of the renewable resources. And also we have storage systems over here, such as flywheels and battery storages. Now, the main DER that we are going to be using or we are going to discussing today is the marine hydrokinetic power generation. So, marine hydrokinetic power generation refers to the renewable energy that is harnessed from natural movement of water, and they use waves, tides, ocean currents, and river flows without the use of reservoirs. The energy is captured through technologies such as underwater turbines, oscillating devices, and which convert the kinetic energy and the potential energy of a moving water. So the US has about a very, very vast and untapped marine hydrokinetic energy resource. The technical power generation has a potential of about 2,300 terawatt hour per year. This is estimated to be about 57% of the total energy requirement of all US states registered in the year 2019. Next, there are two major types of marine hydrokinetic energy resources. One is the wave energy. The wave energy is the one we are going to be using today. We are going to be discussing it vast today. So this is the energy that is captured from the surface of the waves driven by the wind. The US potential is about 1,400 terawatt hour per year. That counts to about 34% of the electricity demand and has the power of lighting 130 million homes. The best locations for harnessing these is Alaska and the Pacific coast. The technologies used are point absorbers, oscillating water columns, attenuators, and overtopping devices. Uh, the advantages are they are a huge resource. They have a high energy density, and the disadvantages are the tech is still maturing. They have an high cost of maintenance because it's an offshore maintenance. Now, I want to show some light on one specific type of technology, that is the oscillating water column. It is a coastal or offshore device that harnesses from the wave motion. So here on the right side, we have a picture over here that can show that the air flows as the wave peaks up, the air flows through the turbine, and the chamber of the chamber here has an airflow, and as per that, the turbine moves. So the oldest OWC is in use is the LIMPET in Scotland with a rated power output of 500 kilowatt hour. This is operational kilowatt. This is operational since 2000. Now again, a little bit on the tidal energy resources. This is a pretty steady source of resource, and it uses the rise and fall of water, ocean tides because of the gravitational force of moon and sun. So as these are pretty much in flow, we have a steady source. This has the US has a potential of about 220 terawatt hour per year. That is about 5.4% of the electricity needs of US, and has the potential to power about 21 million homes. Now we go to our case study of today's case study. So we have taken the location of Yakutat, Alaska. The population of this area is about 562 residents, and they have a total energy need of 4,655 megawatt hour. So here we can this is a completely entire this community entirely depends on diesel generators for electricity generation, and because of this, the average rate of energy rate of this community is the almost 70 cents. So that is pretty high as compared to Alaska, which the average of Alaska is $0.25. That is Yakutat is about 181% more, and for the national average of USA is about $0.15. That is for Yakutat, it's about 366% more. The reason of case study is the geographical advantage that today we are going to be using wave energy. We are going to be seeing a wave energy simulation for this place. And the economic need, again, it's a diesel-based generation mainly, which actually gives a lot of impact on environment, and the infrastructure available. The modernization of Yakutat's power grid for wave integration is also improves reliability and capacity. Next, yes, this is a very important, very particular information that because of which we decided today to go for the wave energy system. Is that we can see that Yakutat, this is the location of Yakutat. This is the location, and this is the wave power. This is the shoreline, and there the wave power we have is about 29.45 kilowatt per meter, and the significant wave height we have over here is about 2.03 meters. 2.03 meters. Now we go on to a simulation. The simulation we have in further simulation we have. I want to show you a little bit of the setup we have today. So the total simulation capacity is about 1 megawatt. The OWC switches on at 20 seconds and continues about 35 seconds in the simulation. The technology used is oscillating water columns, and the rated capacity is about 200 kilowatt. The efficiency range is 20 to 40%, and the type of OWC we choose is shallow water OWC.
Can everyone hear me?
Yeah.
Okay, so I'm going to go over our PSCAD simulation a little bit. So this is a microgrid that we use to simulate Yakutat's power grid. You can see on the left here, we have the main grid. This is where if Yakutat was connected, it would connect to a main grid. At the bottom, we have our distribution control, distribution generators. This is where we're simulating our oscillating wave column. On the right, you have the master generator. This is So this one is going to be
Okay, someone will not hear me anything. 1 minute.
here. I mean, so on the left here, you can see what we used to simulate this wave on the right. So if you go on one, we're using a table to simulate a wave. Then we are putting this through a transfer function and interpolating it to make it look smoother. And if you go on, we're then taking the absolute value of that data to get the average power and then multiplying it by an efficiency factor. And you can see the general equation for oscillating wave columns here. So it depends on the average power output, the overall efficiency, the density, everything we have to take into effect, and this is how we were able to simulate it. So as a result, you can see this is in islanded mode. So the black line at the top in the first graph is the P load. So that's all the power our load is taking. You can see as PDG, the green line in the first graph, goes up. So that's the power we're getting from the waves. As that goes up, the diesel generation equivalently goes down. And then you can see our reactive power change in the second chart. And you can see our voltage change as a result. And as you can see, the voltage is very small, like 0.00025 changing as the distribution generation takes over. You can see that our reactive power is a bit unstable, and this is a potential area we could look at in the future if we continue this project. So this is the same result in grid following mode. So this is if Yakutat was connected to a larger grid. You can see that the complex power in the middle, as the simulation goes on, is a lot more stable. And you can see that instead of the diesel generation being replaced by the hydropower, instead you're taking less power from the grid. So in this simulation, you're taking 400 kilowatts from the grid and 600 kilowatts from the generator.
Yeah. Now we see the Yakutat's the feasibility of wave energy in Yakutat. So at the left, we have the existing energy landscape, that is a diesel-based energy landscape. The overview is again, population is 562. The base load they require is about 750 kilowatt, and the total energy demand is 4,655 megawatt hour per year. So right now the energy cost they have is about $0.69, that is about 70 cents kilowatt per hour, and the annual cost counts to about $3.26 million. The environmental impact that the diesel generator has, they require about 3,500 gallons per month of diesel, and the environmental impact is about 26.9 million kg per year. 100% diesel dependency, and also it is ranked among one of the worst per capita emitter in Alaska. So on the right side, we have a wave energy scenario where about a 1 megawatt OWC is installed at an efficiency of 40%. So the installed capacity is 1 megawatt or 1,000 kilowatt. The output we get from this is about 33,504 megawatt hour per year, and the efficiency at 40% capacity factor. The coverage it gives is it takes over 75% of Yakutat's energy needs. The financial impact it will have is it can save about $2.45 million per year, and the total project, if we take into account the cost of the project, this could be about $16.5 million, and we reach a break-even point at about 7 years. The reduced now after this, we can see that a reduced effective cost is about 0.17 kilowatt hour, and also it has an environmental benefit that the CO2 emission will be reduced and about 20.26 million kg per year, and this causes the emission to drop by 75%. So now in conclusion, we would just want to say that the marine hydrokinetic energy offers a sustainable pathway for remote communities like Yakutat to transition from diesel dependency to an energy independent areas. The islanded microgrids and MHK are naturally aligned. They provide consistent local energy resources suited for coastal areas. The PSCAD simulation demonstrate an effective active power with diesel generation and OWC system together. And with with future improvement, we can also work on the reactive power control. Also, future work would on this project would include integrating other DERs such as wind energy, photovoltaic resources, and advanced storage systems such as BESS and flywheels. Although there is a very high capital cost at the initial level, but for a long-term economic and environmental benefit, they're pretty sustainable. Yakutat exemplifies how strategic investment in marine hydrokinetic energy can actually drive sustainable development, increase the community's resilience. Uh, these are the references that we have used. That's it for today. Any questions?
Yeah, any question, guys, for Sriya and Evan? Who are the members, Sriya? Do you have a list?
So my members are Evan is my member, and Brianna and Zach.
Okay. All right. So this is yeah, this is very good. And you include. Did you finish your report as well?
Yes.
Okay. Could you submit it so that I can
Yes,
post it
yes.
on Canvas?
Yes, of course.
All right. Sounds good. Any questions from the audience? Any questions? All right. If not, then we can close today's presentations. We will have another one on Wednesday, same time, another set of 3 presenters. All right. Thank you very much. Okay.
Thank you.
Bye-bye.